Okay, everyone. I think we're ready to start this keynote. So please. I hope you all have enjoyed the day so far. My name is Yusuf Talbi, and it is my pleasure and honor to present this second keynote at the 20th World Economic History Congress. As you all know, the theme of this Congress is equality and sustainability challenges. Stephen Hawking, the famous British physicist, once said that he believed that the 21st century will be the century of complexity. He said so because we know that these and other challenges before humankind are characterized by great complexity, part of complex systems, ruling out quick fixes or simple solutions. Now, we know that economic history can contribute to these issues, but to understand, let alone address such complex issues, we also need a broad range of perspectives. And we need to apply interdisciplinary perspectives and methods that do not shy away from the structural complexity of the problems at hand. Methods like big data and machine learning can certainly help us do that. Professor César Hidalgo, currently at the Toulouse School of Economics and director of the Center for Collective Learning, has in his award-winning work done precisely this. His research has brought fresh perspectives from complexity science using big data and machine learning to explore important issues, not least the development of nations and inequality. With publications in journals like Nature and Science, to name a few, he has been a leading voice in showing that a country's position in the product space or network of traded goods shapes its path of economic development. He has published 3 widely read and deeply thought-provoking books: Why Information Grows, The Atlas of Economic Complexity, and How Humans Judge Machines. His work has been honored with the prestigious Lagrange Prize, the Bicentennial Medal from the Chilean Congress, and 3 Webby Awards for his leading work on data visualization. So expect really nice slides. Today, we look forward to an inspiring keynote on big data and machine learning, explorations of economic history and collective learning. Please join me in giving a warm welcome to Professor César Hidalgo. Please, the floor is yours. Thank you.
Thank you, Joseph, for the kind introduction. Also, thanks to Matt Olson for inviting me to be here. So I'm going to start with a disclosure. I'm a physicist by training, so I apologize for that. And I'm going to be talking about how we can use machine learning to understand some aspects of history. And I thought that to tell you that story, maybe the easiest way for me to introduce the topic was by telling you the story of the project itself, like how we came to this idea, how we came to this line of research. And I'm going to go back to a long, long time ago in a university far, far away, because in the late 2000s, we were trying to understand the world, we were trying to understand the process of economic development using fine-grained data on the mix of products that countries export. And we were able to create networks that could help us understand how economies developed, what were the products that they would enter or exit, and we could create measures of the value of the portfolio of those products. And as that research became adopted, it generated demand for that type of analysis. Analysis that it was expensive to make. It required a lot of work in terms of calculations and data visualization and so forth. And that motivated us to create observatories that we could use to distribute this data. So in 2011, we launched the Observatory of Economic Complexity, which is a tool that today is one of the main tools in the world to distribute international trade data and allows you to look at that data from a number of perspectives. But the story that I'm going to tell you today is not the story of economic complexity, but a story that stems from this story, because around the time that we launched the Observatory of Economic Complexity, there was something that was deeply unsettling about the way in which we were looking at the world. And what was unsatisfying is that if you look at data, for instance, for Brazil, you would see on the Observatory of Economic Complexity that Brazil is great at exporting iron ore, crude petroleum, soybeans, raw sugar, corn, and coffee. But if you've been to Brazil, you know that Brazil is about much more than iron ore, soybeans, and coffee. You would say, well, Brazil also, it's a place that has produced great soccer players like Pelé, or that has produced famous, race car drivers like Ayrton Senna or Nelson Piquet. It's also a place of great music, and none of that is reflected in the productive structure that we observe when we look at a place like the Observatory of Economic Complexity, or if we look at one of the many observatories that have been created since using Brazilian data, like Data MPE or Data Viva. So that motivated us to create a different type of observatory, an observatory that we call Pantheon, that tried to fill in this gap. So we call this Pantheon. Here probably you would call it Valhalla, because we reason that when people die, maybe yes, maybe no, maybe their souls go to heaven, but for sure, some of what they did gets preserved on the internet. So the internet is sort of like this collective graveyard that is amassing information about the famous people that have existed in our world, and it's becoming increasingly more comprehensive. So that's why we call this site Pantheon, because basically what we did was create an observatory of collective memory that was based on the unit that we thought was the easiest one to create this observatory around, and that was the biography. So you have to remember that in 2012, 2013, LLMs were not around. They were not as good as they were right now, for sure. So what we did is we created a natural language processing tool that we call Johnny 5, in honor from Johnny 5 from the movie Short Circuit, because Johnny 5 was great at reading books and summarizing them. And we launched Johnny 5 over the 300 Wikipedia language editions. And we use Johnny 5 to then start structuring that data. So Johnny 5 would see a biography and would respond a vector with the date of birth, the place of birth, the date of death, the place of death, and also different metrics about how many times these pages were being visited, like the number of page views or the number of language editions in which they have a presence, or the variation of the page views over time. And we use that information as the atomic unit to create this observatory of collective memory in which we could accommodate some of the critiques that we ourselves had made about the WEHC in terms of its inability to understand culture. So let's look a little bit at who is in that data. In the first version of Pantheon, we included only people that had at least 25 different language editions in the Wikipedia. We use that as a criteria because, of course, the further you are in the tail, the easier it is to structure the data, the more reliable the data is. The Wikipedia page for someone like John Lennon is very comprehensive. The Wikipedia page for someone that has maybe one page in one language, is more likely to have mistakes or to be incomplete. And you see that there's a long tail, and we're just grabbing into that tail. At the end of the tail, you would have people that are extremely famous, like Jesus or Barack Obama, who was president of the United States at the time, or Leonardo da Vinci. Then in the middle of the tail, you would see people that are very famous, and you would see that the Beatles come in the right order, with John, then Paul, then George, and then Ringo. And at the bottom of the tail, you have people that we would not consider in this observatory. So the first version was people that have at least 25 language editions in the Wikipedia. The subsequent versions that we've done is 15 or more, which gives us a data set of a little bit over 100,000 different biographies. What was hard about this is that also we had to create a control vocabulary for the occupations, because you would go to the page of Steven Spielberg and it would say that he's a movie director, and you would go to the page of Robert Zemeckis and it would say that he's a director of film. The vocabulary was not controlled, and we had to create it so that we would have that categorical information that, as we're going to see, is going to be very important. But eventually we had now this second observatory, and there were some similarities and some differences. For instance, both of them had this sort of exporter, product, importer type of triads. In the case of the WEHC, Brazil, let's say, might be exporting coffee to Japan. And in the case of Pantheon, Brazil might be a country that produces famous soccer players that are written in the Japanese language edition of the Wikipedia. So it's not perfectly symmetric, because in Pantheon we don't have an importer, we have a language only, but we have triads nevertheless. But what's really different was the time series. In the WEHC we had a time series of a little bit over 60 years. And that is great. There's a lot that has happened in the last 60 years that we can look at when we look at this data. But in Pantheon, we would have people like Abraham or people from ancient Egypt. So we had a much longer time series, and that motivated us to do different things. So what I'm going to do is I'm going to tell you a few stories that are going to explore how collective memory is shaped by different factors. We're going to start with technology, time, and language, and then we're going to move back to the beginning using these biographies to try to understand certain aspects of economic history. So let's start with technology. So a very well-known hypothesis when it comes to the impact of technology in collective memory is that changes in technology might change the type of messages that are being transmitted through different communication technologies. Elizabeth Einstein famously, put that hypothesis, but probably the person that made that hypothesis most popular is Marshall McLuhan. So I want to show you a video in which Marshall McLuhan himself answers to that question.
If the medium is the message, and it doesn't matter what we say on TV, why are we all here tonight? And why am I asking this question?
I didn't say it didn't matter what you asked on TV. I said that the effect of TV, the message of TV, is quite independent of the program. That is, there is a huge technology involved in TV which surrounds you physically. And the effect of that huge service environment on you personally is vast. The effect of the program is incidental.
So the idea of Marshall McLuhan and of other people that have advanced this hypothesis is that as communication technologies change, the messages that are best adapted to those mediums also change, and basically some messages are more fit within some communication technologies than others. So what we remember should change as well. So as soon as we built Pantheon, we decided to try to see if we could observe this hypothesis. So the first thing that we did is quite simple, but you're going to see that there's something in it, is look at the time series. And here you have a time series in which the y-axis tells you the births per year per million people of the people that made it into Pantheon. These people that are really famous. They have more than 25 language editions in the Wikipedia, or more than 15, depending on the edition of Pantheon that we're looking at. So it's the probability, let's say, that your son or daughter will grow up to be someone as famous as Leonardo da Vinci or Jeanne d'Arc or so forth. And what is fun is that for the first 2,000 years, you see that this line is basically flat. The population of the world is changing, but the rate is not. It's quite constant. And then around the year 1450, you see a jump. The number of people that we remember grows. And then around the year, the late 1600s, you see another jump. Now, all of a sudden, this is not flat or going down, but going up, meaning that, the rate is accelerating. And then it even accelerates even further, when we get closer to the 20th century. Now, what is interesting about the Pantheon data is that it allows us to go beyond the time series. And McLuhan's hypothesis is not a hypothesis of just that we're remembering more things, it's that we're remembering different things. So we need that categorical information to be able to see if that hypothesis is reflected in this data. So we can see who is the people that made it into Pantheon for each one of these time periods. So when we look at the year 4000 BC to 1400, like the first chunk of the data, most of the people that we find on the Wikipedia that are really famous are either political or religious leaders. They're kings or noblemen or prophets, or religious leaders and so forth. There are relatively few scientists and artists in comparison. And then we get printing. And I don't think I have to convince this crowd that printing was extremely important. And it really, represents a before and after, in history. The favorite book that I read on that is the one from Andrew Pettigrew on printing on early modern Europe. And when printing came along, the types of messages that could be transmitted in printed media also changed. The world of religious leaders and political leaders was an oral world, but the world of printing allowed a new elite to emerge that included many painters, included composers. Printing affected, the way in which music was being transmitted because it could be printed for the first time and shared. That is even an important component of, the Reformation. And also, it gives rise, to the sciences because now data could be fixed, data could be transmitted more reliably, and also scientists, could accumulate books that they could read to write the books that they were trying to produce on their own. And then you have a second printing era, because printing is a technology that evolves over a long period of time, and it takes a while for people to be able to produce things reliably and fast enough to have now printing formats that are focused on current events. A book can be about something that happened 100 years ago. But journals and newspapers are focused on things that happen more recently, on things that are hot. And when that happened, you have now a public sphere that emerges together with that type of printing, and that involves the rise of the sciences. So if you think about the first, scientific journals, many of them are from the 1600s or 1700s. They get started around that time. And you have now, a pantheon that is quite different from the one that we had in the first printing era or before printing. Now you have a lot of famous physicists, chemists, biologists, and mathematicians and astronomers that come along. The arts continues to be dominated by composers, painters, graphic artists, and so forth. And then you have the era of film and radio. And film and radio also, introduced a transition, but it's a transition that is very important in the arts. Because before film and radio, the performer didn't get as much limelight as, the writer of the play. The actor was secondary to, the screenplay. Everybody knows about Shakespeare, but very few people know who were the actors in that era. So what you have is a change now in the arts in which performers are the ones, that are start to get more recognition. And the art change is not composers anymore. It's not writers or playwrights anymore. They're actors, musicians, and singers, the ones that become really important. And then we have another change in technology around the 1950s, which is the introduction of television. And you might think that television and film are similar, but they're quite different because there's something that you would never go to watch in a movie theater. And that's a soccer game, because that needs to be live, So what happens is that television, of course, you can use TV to watch movies, but you can also go to the cinema to watch movies. But what TV, does is introduces the world, to the machinery of sports. Sports become an important phenomenon thanks to television. Today is the only thing that, TV channels still make money on is news and soccer games. And you have now a world, in which the people that have become famous over the last, 50, 60 years, mostly, are involved in either the performing arts or in sports. So this is a nice descriptive story that tells you that maybe McLuhan was right. As, communication technologies were changing, the composition of our collective memory was changing as well. But can we find a little bit stronger evidence of that? So you know that printing has this very nice property that it started in a place and then it spread from there. And even though, of course, that spreading process has a lot of idiosyncrasies, it is not uncommon to use the distance to minds as a way to instrument for the availability of printing in a place. And what we did, in this paper is we look at the distance of minds as an instrument to try to see which were the cities that were exposed to printing earlier than others. So for instance, a city like Cologne might have many characteristics that would lead them to produce a famous scientist or artist, which are the categories that we understood came about after the introduction of printing, or they became more common. And a city like Porto might have many of those characteristics as well. But the difference between Porto and Cologne is that Porto is closer to minds and therefore is more likely to learn about printing earlier, so it should have a leg up Porto, not because of anything that is particular to Cologne, but because of that accident of happening to be close to the city of Mainz, which is located in the same river valley. And when we do that, we find exactly what we were expecting. So the year of the first scientist or the year of the first artist is very much predicted by being closer to minds, by this instrumental variable, but the year of the first politician, for instance, which was a category that was very popular before the introduction of printing, is not. So that's how technology, it's affecting our collective memory, it's changing its composition. But let's go into the next story, and the next story focuses on time. And that story starts more or less at the same time that the first one, but involves another student, Christian Candia, who was visiting my lab in Boston at that time, and he was interested in music. So what he did is he mixed the data from Spotify with data from the Billboard 100 list, and he came to my office with, this chart. This chart shows on the y-axis how popular a song was in Spotify in 2016 as a function of the date in which it was first featured in the top 100 of the Billboard ranking. And you might look at this chart and say okay, well, grad student is trying to do something, coming up with a chart, who cares? But when we saw the chart, there were two things that I thought were non-trivial about this chart. The first one is this knee that you see around here. Because this is not just a linear form of decay. We don't know what the heck is in the y-axis at this moment. We don't know what Spotify uses to measure popularity, but we see that knee around the year 2011, and that feels strange. The other thing that feels strange is that if you know about attention curves don't look like this. Attention curves look like that. Attention at the beginning is small, then it grows, because there's a period of adoption, and then there is a period of decay. And we were not observing that. We were observing a curve that looked different. So we had two things that we needed to explain. Why was the curve that Christian Candia had done, with his data look the way that it did, and why it had that knee? Now, what happened is that attention is something that has been studied quite a bit in scientometrics. Also, many people in physics have studied the dynamics of attention. And the general consensus is that it is a separable function. Okay? So that means that you have one component of attention that is based on the previous attention that something has received. That's the preferential attachment or cumulative advantage type of component. And there's another component that is temporal decay, which has not been studied as much as the first component, as this preferential attachment. So when you separate this into two functions, when you separate a normal attention curve into two functions, what you're going to get is these two components. The first component tells you that something is going to get attention in proportion to how much attention has received until that point. And then, once you take that component into account, you're going to observe the decay of the attention function that occurs at the margin of that. Okay, great. So now we know why Christian Candia was not observing a traditional attention function. And the reason was that all of these songs that had made it into the Billboard 100 in some way were comparable. They were very famous. It was not a random collection of songs. It was a very biased sample of very famous songs that had received a lot of attention at some point, so they were part of the same subset. But what we haven't explained is why there is a knee or a kink on the curve. So to explain why there is a kink of the curve, what we did is we borrowed from the literature from some anthropologists that actually discuss collective memory as being made of two components. On the one hand, you have communicative memory, and that's the memory that we sustain through acts of communication, like conversation. So for instance, you might be talking about this presentation later today during the cocktail hour, but tomorrow you're going to have moved to another topic because communicative memory decays really fast. We talk about something, but then soon we're talking about something else. But what might happen is that as we talk about things, we might generate content about those things that are occupying our attention during that brief period of time. So maybe someone is going to write a blog post about it. And that starts generating what we call cultural memory. So what you have is a process in which something becomes popular. There's, first a wave of communicative memory, and that leads to the creation of cultural memory. So communicative memory decays by being forgotten or by producing cultural products that then extend the memory and they give rise to the second side of the curve. So that's a relatively simple model. You can solve it with some differential equations from undergraduate. But what was interesting is that we went to apply this model beyond music data. So what we did in this paper is we went to look at any data set that we could find where we could explore whether that data set would have that type of signature. So we look at papers and we look at their citations. We look at patents and we look at their citations. We look at music. We look at movie trailers. We look at the attention received by Olympic medalists on Wikipedia, and basketball players and tennis players and so forth. And in all of them, we find this two-hump function. So the parameter changes. For example, music is forgotten much faster than people. People have like a knee at around 20 years, music at around 5, but the shape is the same. The shape is universal and can be explained by this relatively simple model. The next story focuses on language. And this is a story that is quite obvious, but I think it's important. One of the reasons why I'm here today, maybe not the only reason, hopefully not the only reason, is that I can speak English. If I wasn't able to speak English, I wouldn't be able to participate of this event. Because in some way, if you zoom out and you want to look at the social network of the world, the coarsest scale that you could ever produce is a scale in which you are grouping people based on their language. Yeah? So you can only have friends, you can only have social relationships with people as long as you share a language. Otherwise, it's really hard to develop a relationship with them. So what we did many years ago was map this network of languages by looking at different sources. So this network that you see here looks at languages based on book translations. So we grabbed the data set from the UNESCO that had 2.2 million book translations, and would say, well, if this book was translated from English to French, it contributes to a link between these two languages. And that provided us a network that has a very particular structure, that there's a central hub here that is English, there's some peripheral hubs like French or Russian and so forth, and then there are peripheral languages that connect to some of these regional hubs or to the central hub. And we can do this also looking at Twitter. In this case, what we would do is we would look at the language in which a person tweets. And for example, if I tweet in Spanish and then another day I tweet in English, you would know that this user can speak both languages and therefore contribute to both, conversational spheres. But I never tweet in German, so therefore I wouldn't be contributing to that link. And then we looked at Wikipedia, and we look at the editors of Wikipedia. So if the editors of Wikipedia were editing different language editions, maybe this person edited a page in the English Wikipedia and then edited a page in the German Wikipedia, so that person speaks both languages because he can write in both of them. And when we looked at that, we were able to create measures of the importance of a language, not based on the population, number of speakers, or based on their economic power, but based on the position that they occupy in their network. And when we put these measures together in a statistical model to try to explain how many famous people were globally known in English or in Chinese or in Arabic or in French, what we find is that the centrality of a language in each one of these networks is a significant and quite robust predictor of the number of famous people produced by that language. So English has a privileged position in the world, not just because the US is large and rich, but because it is a hub language. And that really contributes in ways that go beyond the size and the wealth of the United States in this example. But of course, it's not just about global fame, there are also local components. So one of the things that we have been exploring recently is how important is the local premium. I'm sure that there's people that here in Lund are very famous that I might not be aware of. So I'm going to give you the opposite example. I'm sure that everybody can know the person on the left, no? Who's the one on the left? Napoleon. Everybody knows that. Now, anybody can mention the person on the right? No, not Bolivar. O'Higgins. Bernardo O'Higgins. So how many of you have never heard about Bernardo O'Higgins before? So Bernardo O'Higgins is the George Washington of Chile. Okay, so if you didn't know, Chile was, liberated by, an Irishman. And Bernardo O'Higgins in Chile is as known, or maybe even better known as Napoleon. So let me give you some evidence of that. So the main street in downtown Santiago, the largest avenue in downtown, is Avenida Bernardo O'Higgins, of course. There are, of course, statues around the country. Every city would have, a street called O'Higgins. There's a university named after him. There have been, series on television about his life. He's in every coin, or has been in every coin at some point. There's a whole region in the country named after O'Higgins. And he has the biggest honor that anybody can have in Latin America. There's a soccer team called O'Higgins. So fame can be highly local, attention can be highly local, and understanding that local component and the local premium can be hard. So let me give you an example that is not as dramatic as Napoleon and O'Higgins. And that's the one of Lynn Ostrom and Johnny Unitas. So they were both born in the United States, so same country. They were both born in the same year, or 1933, and they were both very accomplished. Eleanor Ostrom, she won the Nobel Prize in economics. Johnny Unitas was a 4 times national champion and Hall of Famer, in American football. And if you look at how many page views they received in Wikipedia in 2022, Unitas was a little bit more popular than Ostrom. But what they had as a big difference was the distribution of attention across these different language editions. So Unitas received most of his page views in English, 91.3% of them, while Ostrom only received about half of her page views in English and received a lot of page views in French, in Spanish, in German, even in Russian. So we can use these distributions to define a measure of local fame and global fame, because clearly Unitas is a locally famous person in English, and Ostrom, even though she's not as famous, in the English-speaking world, she's a more global person. So we can define locality as how popular is a biography in its most popular language divided by the best performer in that language. And if we do that, Unitas is a 0.57, Ostrom is a 0.49, so that's quite a big difference. If this would be percentages, it would be almost a 10 percentage point difference. Globality is the fraction of language in which a person has an above average presence. And here we see a big difference. Ostrom is a 0.32, and Unitas is a 0.05. Yeah? So when we look at these two variables, we can now classify each one of these historical characters as globally famous, locally famous, or both. Sometimes those things go together. So someone like Napoleon is both very well known in French and across the world. Einstein is very known in his best performing language, whether that is English or German, and is also well known around the world. But Bernardo Higgins is more of a local figure than a global figure. Johnny Unitas is also extremely local, a little global. But we wanted to go beyond these descriptive statistics that we can do using Wikipedia data. So we use Pantheon to do an experiment. Because what we have in Pantheon, which is very nice to have, is a little bit of traffic. We have people that are using this platform regularly. So we decided to create an experiment in which we did a trivia game where we asked people to answer questions about famous biographies. So here's a trivial question. John Lennon was a musician, an astronaut, a sociologist, a biologist. And we would assume that if you answered musician, if you provided the correct answer, you are more likely to know who John Lennon was than if you answered that John Lennon was an astronaut. Okay? So we ran this trivia game for many, many days. Every day there were 10 questions and they would change. And what is nice about this game is that when people come into the site and they play the game, they don't choose if they're answering questions about someone that is local to them or that is foreign to them. So the foreign-local dimension, whether they match with you or not, is exogenous to the player. Yeah? So you are British, and if you get John Lennon or if you get to answer a question about Bernardo Higgins, it's not something that you select yourself to. So we could use this to now try to understand what determines that premium. Are Chileans more likely to know about Bernardo Higgins? Or are people more likely to know about others that share a language or that share a geography with them? And when we do the econometrics and we run the model, we do find that indeed there is a same country effect and there is a same language effect, and the same country effect seems to dominate. It seems to be a little bit more important. It's about like 10%, while the same language effect is about 4%. So it's more of a shared country than a shared language type of story. Of course, there are languages that are spread across many different parts of the world, like Spanish has a vast territory, and in other cases, same country and same language coincide very tightly. So now I'm going to switch gears a little bit, and I'm going to start with a famous phrase by Napoleon himself, which says, online data on biographies, traffic, and experiments can teach us about collective memory, but can they also teach us about economic geography? So we're going to explore two stories. The first one is the role of migrants as vectors of knowledge flows. And there's enormous literature that has documented that migrants are extremely important when it comes to knowledge flows. But one thing about that literature is that it usually tends to focus on data on patents or publications, and that data is of relatively recent vintage. Patents haven't been going around for that long, and most of the patents are more recent, and many of these studies focus on the 20th century or sometimes in the 21st century. Data on publications has a bit of the similar problem. So there's a little bit of a movement within this field of the geography of innovation to try to understand these things in a more historical context. Can we go back and see if these things were also true in the 1500s or in the 1600s? Yeah? Well, we cannot use the methods that we have been using or the data we have been using to do that. And that's where this biographical data might come to the rescue. So what we did is we grabbed data like the one that we have in Pantheon about the places of birth and places of death of globally famous people, and we use that to generate a network in which we would assume that the place of birth and the place of death represent some sort of migratory flow between these two locations. We verified that for a random sample of 200 biographies, and we found that for over 80% of them, actually both places were significant places in a person's history. Most of the migration happens actually from small towns to the capital of their own countries, as you can see, in this map. And then we use this to generate a matrix of spillovers. Spillovers could be between locations or between activities, or within locations or within activities. So for example, a migrant mathematician could increase the probability that a place would produce more famous mathematicians. Or a migrant mathematician could increase the probability that a place would produce famous physicists in the future. Yeah? So to formalize this matrix, what we had to do is first, we need to estimate the number of excess immigrants and emigrants that our location was receiving from another place. Yes, because sure, Berlin, Paris, they're huge. So if one mathematician moves from Berlin to Paris, that doesn't mean much. There's, of course, going to be some flow between these two big hubs. But if we control for the expected number and we see that the flow is larger than what we would expect, we have a measure of that excess exposure that would be coming through that flow. And once we have that, we can calculate measures of relatedness for immigrants, for emigrants, and for locals that we can use to then formalize our matrix of spillovers into 4 different terms. Now, when we look at the probability that a region would beget a famous person in a certain occupation in the future, we find that only 2 of these terms really survive. And surviving here is hard because we have a broad category region time fixed effect. So this cannot be explained because there was a university that was built in that city at that century, because that would be captured by that region time fixed effect. Or because a conservatory was built for music, because that would be calculated by the broad category music, region, and time fixed effect. So there's like 700 fixed effects here trying to control for all of these other things. Not perfect, but it's the best that we could do at the time. And what we find is that first we reproduce what everybody in economic geography knows. The probability that a place would specialize in a certain activity increases when you have migrants in that activity. So receiving more mathematicians increases the probability that a place would produce famous mathematicians born in that location in the next century. The emigrants don't contribute, which is kind of funny. So if the mathematicians that are born in that place leave, they don't leave behind, that secret sauce that you need to produce new mathematicians in the future. And the other term that survives is this relatedness term, which means that when new mathematicians, let's say, move into a region in excess, they increase the probability that that region would produce famous people in related activities, let's say famous physicists or famous astronomers, which are related to mathematics. So we could extend this idea of relatedness into a historical context using this biographical data. And the last story that I'm going to tell you is a paper that we published last year that tries to estimate historical GDP per capita numbers using this type of biographical data. And to put it in simple terms, what we have here is a world in which historical GDP per capita estimates are relatively scarce. So if we look at the Madison project by the year 1300, it has 6 data points: Northern Italy, France, Spain, England, and Sweden. Even if we look at the year 1750, the data is relatively scarce as well. So what we wanted to do is to use this as training data to be able to go from the picture that you see on your left to the picture that you see on your right, to create estimates of historical GDP per capita for NUTS2 region in Europe. And how can we do that? Well, what we do is that we are going to build vectors for each one of these NUTS2 regions and for each one of their periods using data on biographies. Because what we do have is 561,000 biographies from famous individuals. We use in this case the Lund et al. Data set, which is similar to Pantheon, but includes more biographies, but less resolution in their occupational categories. And that allows us, to place many people in each one of those regions at different points in time. Now, why would we expect biographies to carry any signal in this case? And I think there are 2 reasons. One is that they could have a direct effect. So if you are a place like northern Scotland and James Watt happens to invent the steam engine there, that might help improve the productivity of your economy. But there might also be an indirect effect. If you're a place that is very rich, like Tuscany, in the 1450s, you might attract people that have talent, and those people that have talent might be able to develop their talent because of the wealth of that location. So someone with the talent of Michelangelo, born in rural Romania in 1450, might have never, painted something like the Sistine Chapel. And what is nice about this is that this is not a causal story. We just care about the correlation. We just care about these variables being correlated with the GDP per capita of that location at that point in time, because that's what we're trying to estimate. So what do? Then we grab all of these features, and we have hundreds of features. So we separate our data set into a training set and a test set, and we train our variables. We do regularization with an elastic net, and then we predict the values on our test set that the data set, that model never saw. And when we do that, we get a relatively good fit. So the values that you see here, this is a fit on values that the model never saw. Okay, the values that were in the test set. So now that we have our model, we can validate it using different type of historical examples. So I'm going to show you 6 examples of how we validated the model. The first one is the little divergence. So it is well known that in 1300s, Southern Europe was richer than Northern Europe, but then there was a reversal of fortune that happened over a long period of time. So we can now look at the data that we estimated and see if it satisfied that pattern. And we observed that pattern very clearly. We observed like a crossover around the middle of the Reformation, in which Northern Europe becomes richer than Southern Europe, because Southern Europe more or less stays flat during that period, while Northern Europe continues to increase. The second example that we use is from Acemoglu, Johnson, and Robinson. So they have this story that countries that had Atlantic trade basically had an exogenous shock when the Americas were discovered, because the discovery of the Americas was much more beneficial for a country like England than for a country like Greece. Because for England, they had a whole new place that they could go to, while Greece was deep into the Mediterranean. They didn't have that same level of access. And we're able to reproduce here on the left, you see the figure that Acemoglu, Johnson, and Robinson have in their paper. On the right, we have the figure that we're able to reproduce ourselves. So the Atlantic ports do go up in that blue line in comparison. And we're able to validate the data using this result as well. Then we look at different proxies for economic development. So we look at urbanization rates. We have a good correlation. We look at the average height of soldiers. We have a okay correlation. We look at measures of well-being that are also correlated. And the last one is church building activity. The idea here is that if a place during the 1300s, 1400s, 1500s was producing more cubic meters of church, is because they had some sort of excess income that they were able to put into that activity instead of other activities like agriculture. So after doing these 6 different validations, we can now look at the maps of Europe, and this is the story that comes along. So in 1300s, we don't have a lot of estimates, but we have more than 6, which is great. And we see that Tuscany appears as the #1 place in Europe in terms of GDP per capita among all of the estimates that we have. And then as the 1400s move along, Italy, it's really on fire. But then in the 1500s and then in the 1600s, we're going to see other poles emerge. For instance, now you're starting to see that the Netherlands is starting to get dark green as well. And the Netherlands really becomes important then in the 1600s. Then in the 1700s, you have the Netherlands, you have northern Italy, the capital cities like Paris or Madrid are doing better, London is starting to do well, and then when you get to the 1800s, we now finally have estimates for the United States. Funnily enough, when we look at these estimates, we find, for example, that at least you can take this with a pinch of salt, because these are predictions, these are not raw data. But we predict, for instance, that San Jose or also Los Angeles in 1900s was richer than most places in Europe. So that we're already leading in terms of GDP per capita. And with that, I would like to conclude. So I'm going to summarize a little bit, because a long, long time ago, we began building observatories of economy and memory. And when we did that, we learned a few things. We learned that just as products and industries are imperfect but useful proxies of the geography of economic activities, biographies can be imperfect but useful proxies that we can use to explore history. Trust me that doing this research has not been easy. We have been pushed around for a long time, trying to get these things out and improving the techniques. But I think overall, the evidence starts to add. And the message is not that, but the message is one that is more collaborative, and it's the following. Is that more important, this is not about the data or this is not about the methods. Is that we live at a historical moment that grants us with an amazing opportunity to collaborate across disciplines. We're living at a time that is filled with rich data sets and fantastic models. Data sets and models that require people with multiple skills to be gathered and to be manipulated. And the provocation for everyone here in this room is to embrace the opportunity to collaborate across these disciplines. Machine learning is a telescope. We can use it to look at the future, and a lot of people want to predict, how the economy is going to do using machine learning. But at the same time, we also have a lot of gaps on our understanding of the past, and we can use this telescope to point at the past as well and to try to use it to fill some of those gaps too. So the provocation is for us to embrace this opportunity to collaborate across disciplines that this data and these methods provide us. Thank you. Yeah. Thank you.
Can you hear me? Yes. Thank you very much for this very thought-provoking and inspiring keynote. I'm very sure that we have plenty of questions. I am told that there are runners or members of our staff that will collect questions, so please just raise your hands if you have any. I have one here and one over there.
Thank you. Absolutely fascinating and very inspiring. And I'm sure you get asked this question every time, but what do you do about the biases against women represented in Wikipedia and against minorities represented in these sources?
Yeah, so that's a good question. And what you do is you embrace them, because at the end of the day, you are not claiming that you have a perfect representation of the past. You have a representation of the past that comes through a certain lens, which in this case could be the Wikipedia data. Other people that have done similar research, they've used data from encyclopedias and so forth. And you can now try to use this data to try to explain, where those biases are located and what might be the things that cause them. So for instance, you can ask, are those biases or this representation equally across all of the occupations that we have, or across all of the countries that we can observe? And if they're not, now you're going to start thinking about, well, what are the hypotheses that explain that variation? So I don't like to think of like data being biased, because all data is biased. All lenses have aberrations. But studying the aberration of lenses is also part of science. So if you embrace it in that way, there's a lot of excellent questions in that space.
Hi. Thanks a lot. It was extremely interesting. I'm here. I was wondering if you think there is some value in doing what you do, but for non-living things like buildings, infrastructures, structures like bridges or anything that also carries some information in the economic activity, and it's maybe living longer than the memory of human.
Absolutely. Yes. So there's some attempts. I haven't seen them come to fruition, but some people have tried to, use this type of approaches by looking, for instance, at the history of buildings. And of course, buildings, they have a whole set of complexities when it comes to their categorization too, which architectural style or which materials they use and all of that. And if you're able to do that reliably and understand also what were the buildings that were filtered over time, because you have a lot of filtering in a city and in architecture, you might have a very interesting scope to understand the diffusion of, for example, knowledge on different trades that were required, to produce buildings. I travel a lot, and one of the things that I always notice is the architecture and how you have these changes in architecture or construction styles as you move between one country to the next, or sometimes when you cruise a boundary. And those are reflections of the local knowledge, because you never hire a contractor that is 1,000 miles away. Like construction is a very local activity, and therefore it's a very good proxy to understand local practices and knowledge, at least within that domain. It's also usually a big part of GDP, so that also makes it, even though it's particular, it's not, an accident, it's not something minor.
Hi, thank you. So what you have is an image of the memory or the cultural sort of memory of the, say, 1990s to 2020. But what I'm not very clear about, so how do you get to GDP in 1400? Because obviously what would have been the memory of the 1400s and 16th century would have been different. So you would have a different geography if you say, look at what you had in an encyclopedia of the 16th century. So how do you, what you're saying is our image of the 14th century.
Yeah.
So how does that relate to GDP in the 14th century?
That's a good question. So let's start from the fact that we're using data from Wikipedia, and Wikipedia was edited primarily starting in the early 2000s when it exploded, and I think a lot of the Wikipedians that are still edit are more or less the ones that got started in that era. But where did they get started from? They get started from records that had made it until that time. For example, encyclopedias or other written sources. And where those were made from? They were made also of records that existed before. So it's not that when you look at data that was produced in the year 2010, you don't have any information from the past that has made it into that present. In fact, like what you have is this strong filtering that if we're still talking about Leonardo da Vinci today, is because there is a continuous link between Leonardo da Vinci and cultural artifacts and written work that has been produced to describe his work that has survived until today and that has been rewritten and recopied and amplified. So these are not disconnected things. Yes, I would agree that in the 1600s things would have been different, but whatever we have today has to go always to sources that were there before. So by induction, you're going backwards in a way that is continuous.
Hi, sorry, I think I'm the next question in line. I don't know whether I should go now. But,
go.
So my question is another selection bias question, but from the other side, which is using the internet. Who has access to the internet? Wouldn't it be the case, for instance, especially we're trying to understand collective memory. This is collective memory of people who have access to technology. That means collective memory of richer people, generally speaking, and collective memories already of countries with higher GDPs. Is there a way in which you can sort of deal with that problem and trying to especially estimate things like, I guess when you're looking at GDP, but also the significance of certain events in history?
Yeah, so there's two things. There is this prevalent myth that technology exists only in the rich countries. There are more countries with access to the penetration of cell phones in Africa is much larger than the penetration of plumbing, that the penetration of clean water, that the penetration of most of the services that we would consider advanced. So in some way, if we were going to consider a technology that is extremely democratic and available, there's no technology that is more available than the internet when we compare to other technologies that we would consider as proxies of development. And the second thing is then, well, if we look at this, let's say that what is our expectation of the non-biased world? Would in the non-biased world, we would expect the cultural output of Ghana to be equivalent to that of France? Would that be a good reflection of reality because we're equating the number of famous people that we're going to count per population or per country? Or do we expect to observe some of those differences and the fact that maybe in some places people are being recorded less or their stories are not told as much? It's actually a reflection from the fact that their communication systems or their technology are less developed, and therefore that silence, that missing data is informative of these differences. It wouldn't go against this difference, it would be informative because in some sense the recording bias should be correlated with GDP, shouldn't be against GDP. So I think those are like the two things. First, the internet is much more widespread than people usually tend to believe. I don't know why. I think that's something that was left from the 90s when there were differences, but those differences have erased a lot since then, almost entirely. And the second one is that the bias would go in favor of determining differences in GDP because the places that are more likely to get recorded are more likely to be the places that are rich, and that actually would be a good thing for the data.
Thank you very much. So I was interested in survivorship bias. It sort of seems like the Pantheon is a product of sort of a cumulative baton race where every generation receives memorable people. They then filter out who they don't think is memorable. They add people from their period, and then they pass it on. And so then when we get to the present day, if you're looking back at, say, who did people in 0 BC care about, you're seeing it through the lens of all those subsequent generations.
Yes.
So, how do you deal with that, I guess, is the question.
I think the same as everyone else. I don't know, how do you guys deal with that? Like, you can, of course, try to find primary sources that then would get added to a place, you know, like a book, and then eventually would make it to a place like the Wikipedia, and then would make it to the Pantheon. But there's things that you cannot observe. Now, what you can think of is that if, you know, those processes are in some way correlated, there might be signal about the potential availability of people that you have not recorded in the information of the people that were recorded. So just to give an example, there might be a lot of famous Greek philosophers that were really famous at the time of Aristotle, maybe even more famous than Aristotle. There's people that says, you know, these guys were not really famous at that time, that might not make it to the Pantheon. They might not have 15 language editions in Wikipedia because they're not well known today. But the presence of their other philosophers might be evidence that there was a milieu there, and therefore carries indirect information about their presence. So as long as the presences are not purely random, as long as they're correlated, then that's what these methods are going to be able to do, is they're going to be able to extract the signal out of those correlations. And I think it's reasonable to believe that our world is not random, that there are processes of knowledge diffusion and accumulation, there are complementarities between people that would induce these correlations, and therefore we should be able to recover some of that information. Now, always, you know, with a pinch of salt, because there's of course information that gets lost. But the fact that the data would be correlated would mean that not all of the information is lost, because some information is carried implicitly in the information about others that have been recorded, even if they were not recorded. There's 2 questions in the front, and 1 up there.
Which one was it?
What about the people who are not in the Wikipedia, who are not famous? They have also their life and the right that their memory will be respected in history. And I think your telescope will not find them.
No, like that's a great question, because yes, the people that are in the Wikipedia are more than the people that were in the encyclopedia. So that we can agree. The Wikipedia has, you know, hundreds of thousands, if not millions of biographies. So it's increasing. In 100 years from now, you're going to have the records from social media, which are going to be even more comprehensive than the records of Wikipedia, at least for the people that were alive when that technology was available. So history, in some sense, it's not, you know, stopping, is becoming hyper-history, in that now more individuals are being recorded into the books of history because more individuals are involved in the production of content. So the telescope keeps on getting better. Like in 100 years from now, let's say if there are records of everybody that had a Facebook in 2009, you might have a much richer picture of 2009 than you have a picture of 1809, because you don't have that type of data, you know, for 1809. But you're going to have it for 2009. You're going to have information about the social networks, about how frequently they post, about what they talked about, you know, etc. So I think the telescope is moving rapidly on that direction.
Yeah, thank you very much for a very thought-provoking presentation. I was curious about this, the nuts to estimation of GDP, of regional GDP, and I wondered, the figures that you come up with using this methodology, how do they compare either to, you know, studies of particular regions by economic historians where they've made estimates with different methodologies about regional GDP, and also what happens if you extend this methodology into a more modern period where we have what we would generally think of as sort of conventional measurements of regional GDP that we tend to think of as being reliable. What do we find?
Yeah. So that's the first part of the paper. So what you see here is a comparison, from one of the many runs. We have many runs of this model, but this is a run for estimates that were produced by economic historians but were not used in the training data of the model. You see? So that's how when you do machine learning, you have to kind of separate the data in a training test and a test set. And that test set is not used for training, so therefore the model cannot train to the test. You don't want that. That would be bad because it's going to overfit. Okay? So what we do is we train here, and then we find that on average we get like 89% R-squared, 91% R-squared. I had another figure that I removed because it had more detail, but I had the whole distribution of running this hundreds and hundreds of times, and it does very well. So it's exactly what we're doing. We're basically grabbing as much data from economic historians as we can. We use that to train our model, but we separate part of the data into a test set. And we separate the data into a test set in such a way that also we try to avoid contamination. So for instance, we would separate data in such a way in which we're not going to leave the data for Salzburg in the training set and going to put the one for Vienna in the test set because they're within the same country, so they might be too correlated. So we're removing full countries at a time to make sure that we avoid kind of like those spatial correlations, and they could provide, the model an ability to predict that would not be desirable, that might be coming from, data points being particularly correlated because they're too similar to each other. But that's exactly what we do.
Hello, thank you very much for your fantastic presentations. I have two questions. The first, I think, if the data is representative, as you presented, and I think it's a very good data set to study the regional gender inequality issues in the long run in different places in Europe. I don't know if you think about this. And this is the first question. And second one is, I noticed that there's a big chunk area is missing from the analysis, which is Middle East and East Asia. And will it possible to apply the same methods to Middle East and East Asia, for example, to analyze the great divergences between China and Europe? Thank you.
Yeah, so that's a good question. So the reason why, for example, we didn't do Latin America, Africa, Middle East, and East Asia is because since we anticipated a lot of questions about the data and the selection and so forth, we say we're going to focus on Europe and the United States, which are the ones that people kind of like would sort of agree that tend to be overrepresented in these data sets. To develop the methodology. But there's nothing stopping us or you to try to apply this methodology to a wider context and see if it works. At the end, it's an empirical question, whether it works. There might be like great sources similar to Wikipedia in Chinese that might not be available, in English, but that might be available, in China, and that might have excellent information about the economic history of different regions in China. So I think this could be applied, and the question of how well it works or whether, it provides the right differences and estimates that are within the right confidence intervals. It's an empirical question, and in the first paper, we decided to introduce the methodology in a narrower context simply because we thought that was easier to defend as a way to introduce the methodology for the first time.
Yeah. Okay, and with that, I think we have... Oh,
last question,
yeah.
sorry.
Okay.
Yeah, I think the issue with GDP is that if you look at this graph, you only have points in the 19th or 20th century, if I'm correct, and it's likely that the relation between GDP and famous people is not stable over time. And I don't think you have any ground truth. I mean, we know very little about GDP in the Middle Age, so if you predict something based on the relation in the 19th century, and then on the famous people in the Middle Age, we cannot check. We don't know if it's correct or not.
No, yeah. The thing, like, I would have to go and find another slide for you because this slide is not a comprehensive example of everything that we did or every run that we run. No, so we have thousands of times this slide for different time periods and different type of things, and that's what we're using for the assessment. So if you think that what we did is we run one correlation and we say we're good, and then we go and run the validations and they happen to work magically, that's not how this works. But the way that it's easier to communicate it is to show you one slide to say, look, this is what it gives for one example, because if I would have done a talk about only this presentation, yes, I could have gone through all of the details of all of the different technicalities that we do, even how the regularization works, which here we gloss over. So I don't think that's a fair criticism because it's assuming that the slide is a comprehensive representation of the work. If you go, there's about 60 pages of supplementary material with the paper that go through a lot of these details, and you can explore them as well. Unfortunately, I deleted that slide, and I think it's not in the service of the audience to try to look for the other slide, in the middle of the stage. But I can show it to you later if you want. Yeah.
Thank you very much for all the excellent questions.
Thank you.
Thank you. I will just allow myself to ask one final question, given that there are many PhD students and younger economic historians that are interested in big data and machine learning. Because you ended on this very nice note that on a call for collaboration and interdisciplinarity. So I was just wondering if you could very briefly reflect on what do you think are the biggest opportunities with big data and machine learning, and what are the obstacles that lay before us?
Yeah, I think I'm a big believer that science progresses in a way that is extremely gradual, and that we're never right, but we're always getting better. There is the great example of like the measurement of the mass of the electron, and it took a while to converge. And now we know it with great precision. In physics, there's a lot of numbers that it took us a while to, and it's not that they were wrong in the beginning, it's that they were the best estimate that we have, and they're getting better. I think now we live at a place in which, if working, with Wikipedia data as we did last decade to produce this type of results, it's something that could be improved. We're just in the beginning. I think there's a lot that can be done by using machine learning to structure and collect new data sets. LLMs are getting better by the minute, and there's a lot of work, I think, even on evaluating the quality of the LLMs and how it changes over time and how well LLMs know about different periods of history. That's something that is interesting as well. I think there's a whole green field, and be creative. Don't be too afraid, because sometimes it's going to take time for the work to catch up to what you are doing if you're a student. Yeah.
So thank you. And on that note, there's a mingle downstairs in Teknirsala. Thank you very much once again.